We have a great kickoff speaker. So Peter Littlewood started at Bell Labs and then went to the UK for some period, and after Cambridge came back to the US, spent some time as the lab director at Argonne, and then I guess in 2017 went back full-time to being faculty at University of Chicago, where he's now chair of the physics department. And there's a long list of accomplishments, which if we weren't starting a few minutes late, I would list, but as it is, I will say let's look forward to an interesting talk, and thank Peter Littlewood.
Thank you very much for coming, and apologize for being late. I didn't realize how easy it is to get lost on this campus.
In this building.
Yeah.
So I want to sort of list a set of apparently disconnected topics that I really want to talk about. And as I say, this is clocks and flocks and Bose-Einstein condensates and maybe neural networks, and I'll try and get through some of the things. And I'll start very quickly with trying to tell you some of the background physical ideas of this, but I'd also say that if you want to hear a much better talk on this subject, Vincenzo Vitelli is visiting on Monday. So I will try and stay on the quantum side of this problem, because Vincenzo, I think, will talk very much about the active matter, although I will talk about both. This problem has a long history. I always ask people to guess, who is this guy? It's Huygens, actually, that's right. Yeah, you know, a child of the 60s, you can tell by his head. And
they didn't wear wigs in the 60s.
60s, all right, just don't check
But this is a story, by the way, that many of you will know, but I want to bring it out for two particular reasons, but as a bit of history. I think this is the first serious experiment in what we would call modern dynamical systems. And Huygens actually was a clockmaker, amongst other things that he did. He had patents on the pendulum clock. He was actually, I think, the second foreign member of the Royal Society. The Royal Society was founded around this time with the restoration of the monarchy in England, sorry about the history. But the whole point of it was the king had discovered that scientists might be useful. So he wanted to bring them under his wing. And in particular, Huygens got given a research grant, which we would really now call a military research grant. Right? And his research grant was to make good clocks. It intended for maritime pendulum clocks, because it was well understood at this point that a very good way of measuring latitude would be able to tell the time very accurately. And so his job was to make a really great pendulum clock, and in particular one that was right on a ship. So he went off to do this. And as always happens with these things, he discovered some unfortunate things. And this story, if you don't know it, is wonderfully told in this article, actually, by this group here, many people are known to them. So what you need to know is that he made his clocks in pairs. He tried to make two identical clocks. And the reason he made his clocks in pairs was that he had no method of telling the time other than to try and make two identical clocks and determine their accuracy by comparing one to the other. Right? Or you could wait for 24 hours and hope that the sun was up, or something like that. So he made them in pairs. And you know, here's the diagram on this paper, and he discovered something very interesting. He said, no, that if things were very quiet, the clocks, which he knew were going to beat at a slightly different time, would in fact synchronize. And he said consonorant semper reciprocationis particularly, which basically means they synchronized out of phase. And he reported this to the Royal Society. And by the way, he deduced the fact that you know, he'd been cheap on his wood, And so he made these two things in a common frame, so they were coupled. And so he deduced that there was some coupling between the two, which had led to this synchronization. What he called imperceptible movements of the common frame supporting the clock. We would now call them phonons. This is a kind of remarkable discovery. It was a bit of a problem, by the way, for the research group, because when the paper was read out to the Royal Society, the members of the Royal Society said, well, look, your clocks are so bad that one clock can change the time of the other clock. And this wasn't what we paid you to do. So as far as one can tell, the funding wasn't renewed. This is a not uncommon experience with this. So I wanted to illustrate this. Occasionally I carry the pendulums around, and some of you will have seen this, but there is a good reason to show this. And so this is actually an experiment done on my kitchen table with two pendulums, a shoebox, and under here two soda cans. The pendulums are both set to 208, but you can see that even though these are pretty good metronomes, they're not lining up. And you can hear them as they tick, they're gradually beating, they're ticking out of phase. And of course the table isn't, it's pretty rigid. So now as long as they don't mess this up, we'll now couple them. This works really neatly, actually. And of course you can actually see what's happening. They've now really synchronized with this. And the way they're synchronized, of course, is that the box underneath them is rocking from backwards and forwards. Yeah.
They're not 90 degrees out of phase.
Thank you. Exactly. What happened? This thing synchronized in synchrony. Huygens now synchronized out of synchrony. So one of the questions in my talk is going to be, how do you go from one to the other? So is there some kind of dynamical phase transition between one and the other? And I'm going to try and argue that there is, and it goes by virtue of an intermediate phase, which actually has PT symmetry breaking as currently symmetry mode. So I'll try and convince you of that, but this is one, which is there. So this is one reason for putting this up, and to actually provoke exactly that comment. And by the way, it's much harder to get them to synchronize out of phase. So fundamentally what you need to do is this is inertially coupled and it works very well. If you want to get them to synchronize the other way, you have to put them on some floppy substrate so that the coupling is essentially elastic. So inertial coupling is easy to do, but I've never actually managed to make something which will do the Huygens thing.
Well, apparently you have to just put them in the same housing.
Yeah, somehow, right, but it just, right. So anyway, so what is required for this to happen? I think we know. We need to have oscillators that are non-linear, so the amplitude should not be small, because linear oscillators are just going to beat. So that's one reason for using mechanical metronomes, because the amplitude is quite large. And if you ever try this, you'll discover it works better with setting something on 208 rather than on 60, because it's a non-equilibrium system. It's a steady state which is between a balance of driving and dissipation, so there's some loss, which happens as things move around. But of course, these clocks have been wound up so that they're periodically pulsing. And there exists periodic states that are stable to some small external perturbation. And indeed, can one make transitions? In fact, we know this. By the way, this particular problem, even with the detailed level of Huygens clocks, has been very heavily studied. So you can reduce those equations to 6 or 7 ODEs. And there's all kinds of crazy things that can go on in this, as well as the synchronized states. There's certainly chaos. There's also situations where all of the energy transfers to one clock. And oddities like that. So that is sort of a warm-up for the topics, which is, are there phase transitions between different kinds of states, and how does one describe those? Is this synchronization, if I expand it to not just 2 metronomes, but infinite numbers of metronomes, which one can do in physics, if this really is this equivalent of a critical point in an Eddy-Body system. So I'm thinking of critical point in the language of liquid to gas transition, where I know that at that point where I'm transitioning between two phases, I have, if you like, universal fluctuation mechanics. And then something which is more my history actually is there a synchronous connection between quantum systems which synchronize and synchronization in classical models? And that's the second reason for showing that. Just switch the phone it's, if you like, quantum mechanical systems. And that's the second reason I showed you that example, because there is a very good quantum model of those pendula. I can take the pendula and I can replace them by atoms. And in my case, the atoms will be two-level systems, things which could be excited up or down. And I will put them on top of a box, and my box will be an optical cavity. And there's a model, which I'll show you in a moment, whereby you have an exchange, of course, between an electronic excitation which emits a photon, which is then absorbed by the other cavity and comes backwards and forwards. And that's a model that is actually well known and we use to describe actually condensates. So these are the three problems I want to talk about, and I may talk about some more. So as I say, I'll go next to the quantum condensate, and this is actually just a momentum distribution of atoms, in this case actually the atoms are the photons in the cavity, to models of bird flocking, to things that you can build with robots, and finally, possibly, very simple models of neural dynamics, which I think are all governed by some simple things. So, let me just put up some things to try and make a point. Thermodynamic phase transitions we're used to thinking about in terms of, say, models of spins. So these are little spins. I've written down a model which we'll call an XY model, where the spins can just point at some angle in the plane. There's some Hamiltonian, just classical here, which minimizes the energy. And so given an arrangement of coupling constants, I can ask what's the arrangement of spins. And if I do something which is quite simple, to say all of these coupling constants are the same, then I can get a ground state which is a ferromagnet, where all of the spins point in the same direction. But I'll remind you that even if they point in the same direction, that direction is undetermined by this. And so there's one remaining degree of freedom, which goes all the way around. And because this is proper physics, this J in a quantum system has to be emission, or in a classical system it has to be symmetric. Namely, the interaction of spin J with spin I is the same as the interaction of spin J I with J. If I take a dynamical system, like this one, I'll typically assume some kind of equation of motion, which is of this form, so d by dt of the spin, depending on coupling to its neighbors. So this is an equation of motion. I don't necessarily have a Hamiltonian. In particular, this interaction can be generally non-Hermitian or non-symmetric. But for example, if I take something like this, where the W's, say, for example, are all the same, then I can go, and I should say I need to add noise typically in all of these things. I can go from an unsynchronized state, which is fluctuating at some natural frequency where they're all different, to a synchronized state where they all rotate together. And this is familiar in a large class of systems, Kuramoto models being the specific one. So we could tune parameters in here, which change the roundness of aligned to anti-aligned and maybe make more complicated things. And by the way, this is a very well-trodden theory for low-dimensional dynamical systems, and you know this, I'm sure, in this room much better than us. Where if I make a transition from one state to another, it will be a bifurcation of some kind. Perhaps from a stationary state to a limit cycle, or from a limit cycle to chaos, and various other things. Well, I said that the focus of my thinking here is going to be to do that kind of thing, but in a system which is large. Right? So rather than having a few degrees of freedom, it in principle has many. Okay, so let me write down that model. And this is how to think about it. And so this describes the physics of what the physicists call barytons. So you take atoms, and atoms have energy levels. These atoms in the blue are in the ground state. This red one is in an excited state. And I will put them in a large optical cavity. I will have them communicate via some wave-like photon mode. And the excitation spectrum I start with in this model has two things in. I've got modes in a cavity, so this is a photon mode. So photons, as you know, have a light cone. But if I fix the minimum wavelength in one direction like that, the spectrum is a parabola. It's a section of the light cone at some point, so it's something that looks like this. And then these things, which are called in this language excitons, but they're just excited atoms, have essentially no dispersion at all. It's a function of momentum. They're just localized states. They mix because a photon can be absorbed and kicked up to the excited state. So I lose a photon and I gain an excitation here. That could hop back down, and then that excitation could propagate somewhere over here, and they could be connected. And if that happens in a fully wave-coherent fashion, I'll get two hybrid modes. And so these hybrid modes will mix, and so you'll get just literally a wave equation with a 2x2 diagonal coupling. I'll get a mode with a dispersion that looks like that, and a mode with a dispersion which looks like that. And these are given the name polaritons, and the wave functions of these things are just some linear combination of exciton and photon. They pair. So then you look at something like this, and physicists like to look at things like this because here I've got a parabolic dispersion. These things are basically bosons. I should be able to drop atoms into this dispersion, and because they're bosonic, I may be able to get a Bose-Einstein condensate. There may be a very sharp peak here, which sits near the origin. And one of the reasons it's interesting here is because the mass of the particle, namely the curvature here, is small. Rather than doing this with rubidium atoms, when you need to go to nanokelvin, if you want to do this with these kind of atoms, you can do it at room temperature. And it actually is, effectively, as you do this, it builds up a sort of coherent excitation that's like a laser. I don't know whether you want to see this, but I'll write it down in case somebody likes Hamiltonians. So what is this model? Just to be clear, I've got photons of a particular energy. I've got these excitations, which I'll describe as spins. And then I can absorb an excitation and destroy a photon or do the other one. And this has a whole bunch of conservation laws. And actually, in the limit where there are very many atoms and only one cavity mode, it turns out I know the ground state of this Hamiltonian. It's a coherent state. It's like a BCS superconductor. So that this is, I don't want to go into more detail about that because it persists, however, when the system is pumped. Just to show you that it actually does work, these are some experiments. That's measuring that momentum distribution. Very sharp spike here. Change in the spectrum, so-called von-Lübov modes. Demonstration of coherence in vortices. Because it's two dimensions, there's power laws of vortices and things like this. So I don't want to focus on this. This is just to try and convince you that there are experiments that show you this work. Now, here I want to get to the fact that I'm making a condensate out of a two-component system. And those two components consist of my atoms, the pendula, and my photons, which is the box. The modes that I've written here, if I look at these two modes, this is a mode where those two things are in phase. This is an orthogonal mode where they're exactly out of phase. I call this lower and upper baritons. And a conventional low-energy BEC is the solution of some model, which is going to give me a condensate which lives down here. And that's more or less what I showed you. But there's no reason that you couldn't have had a condensate which lives up here. Remember that I'm dealing with a non-equilibrium dynamical system. I don't have to find the absolute ground state. I can find conditions on which I could pump up here. So this is the same thing. And actually, if I want to solve the simplest equation for this, let me go to that before I'll write down some Ginsburg-Landau equation I'm familiar, is that a condensate here and a condensate there both have the same broken symmetry, macroscopically. They are, of course, internal degrees of freedom where they're out of phase, but both of them, when I decide whether they're in phase or out of phase, the absolute phase is not known. And so that's the broken symmetry of the problem, and it's the same for both of them. So that means that I should be able to think of a problem where I have some parameters in the Hamiltonian, or the pumping and the damping, where I can make a transition between those two phases. And because there's no change of symmetry in here, that transition can only be a jump. However, and so this is very much like liquid to gas, where there is no difference in the symmetry between a liquid and a gas, but indeed you can have a phase transition, a first order phase transition, which is a jump. But also there has to be a path around that where I can continuously transform from one to the other, and therefore there is a critical point. And we'd like to explore the fact whether one can have exactly the same thing happening in here. These two phases, one condensed down here, one condensed down there, are not symmetry distinguished. Now, the other thing which is important to realize is how could this actually happen? When this BEC is down here, there's an energy axis, and this, like a laser, has a characteristic frequency at which it oscillates. So this is a synchronization. And there'll be some laser light, some synchronized light, which is here. If you go from here to here like this, they just jump to another frequency. And that's perfectly fine. If I want to find a point like this, I have to find solutions in the vicinity of that where these two states would become degenerate. And that is generically called an exceptional point. I have a non-Hermitian matrix that I'm going to solve, and I'll show you in a moment. And non-Hermitian matrices, of course, don't have real eigenvalues necessarily. And of course, their eigenvectors are not orthogonal. And if I want to get two oscillating solutions, which have to be at the same point, I need to bring those two solutions to be identical, which actually means also that the eigenvectors will become identical as well. So there's a Jordan block which will connect these things. By the way, this is evidence that it happens in experiment. Turns out as you pump, you can sometimes see a sort of continuous transition, sometimes you see a jump, and therefore, presumably, somewhere between this and that, you can find a phase. Let me be a little bit specific about this, about what kind of model are we generically trying to solve. So the model is a time-dependent Ginsburg-Landau equation, d by dt of some wave function, macroscopic wave function. Mixing the two components, light and photons, and in the presence of noise. So I can think of this as just the light component. So this is a system which has a natural frequency, some damping and some diffusion. I have the exciton component, which has, again, its own natural frequency, which is different, some pumping, because I'm adding excitons into the system. Again, some diffusion and some saturating nonlinearity, because the particles are on top of each other. And this is the coupling matrix element between the two, which is the thing which hybridizes the two modes. So we'll take this as a kind of a generic model and look for generic solutions as I tune, in this case, two parameters, typically the loss and the pumping. And of course, what happens is that you can see that I'm looking for stationary solutions of this. So stationary solutions meaning that psi oscillates with a characteristic frequency, e to the I omega t. Omega has to be determined by self-consistent solutions in here. But because this is a 2x2 system, some of the time you'll get more than one solution. And this is what that looks like. So as a function of parameters, one of which actually is photon number, another which is loss. There are regions where I can in fact find two solutions of those equations. So this is dynamic, so I don't know which to occupy. It depends on history, and I can get a jump between the two. There's a point where this merges, and this is the so-called exceptional point, and beyond that, the transition is smooth. So I hope that's clear. Right, so understand that what's special in this system is that I'm having a transition between two different synchronized states. So I need synchronicity to be, I need to find those synchronous solutions, and then I need to decide which one I can have. Once I've got this, then one can explore other things. This at the moment is mean field. I'm not playing anything interesting with gradient terms. I can now ask, what does the spectrum of this solution look like if I make perturbations about the stationary state? So I've got a stationary state where everything is synchronized, and I'm now going to look for wave-like solutions about that. Familiar spin waves, Bogoliubov modes, all of those things. And I know, because there is a U1 rotation symmetry associated with this order parameter, that there must be a Goldstone mode. Namely, there's a mode where this overall synchrony of the synchronization is varied over very long wavelengths, and that's an acoustic mode of linear dispersion. And at a conventional critical point, by the way, I would normally then have another mode which is associated with the anti-symmetrized things of this, which would always be orthogonal to that. And so then what happens at a conventional critical point, there's a massive mode which gradually becomes gapless, and is always orthogonal to this mode. This transition is different because, trying to draw it here, if I'm far away from the transition, these are not orthogonal, but they might be quite different. But as I approach the transition, they become the same. So so for example, if I just think about the dynamics, I may have something like here, which I regard as a potential, but I can't kick it up the hill. Any force I apply on it comes out at an angle, and these things merge. That actually has effects on the dynamics, and I'll just point to it and then not say much more. To imply that the dynamics are different. So we know, for example, in 2 dimensions, that if I now calculate the fluctuations as a function of angle for these modes, I said the modes are acoustic. So this is just averaging the phase fluctuations, and this basically goes like the power of the dimension here and whatever k squared. And that diverges in less than 2 dimensions. That's what we know as the Merlin-Wagner theorem, which says that we can't have long-range order of a model with continuous symmetry in less than 2 dimensions. At the moment you do it now, where now I've got 2 modes, both of them are acoustic, we somehow shift that dimension to 4 dimensions. I don't know whether that's good news or bad news, but the implication actually is that these models are in some sense going to be generically unstable in dimensions less than 4. And therefore we would need to understand what would happen. And by the way, it turns out you can do a normalization group about the upper critical dimension late, which I don't think is helpful, so I won't tell you about it. I want now to realize I'm connected to the internet. We'll find out. That was all quantum mechanics, but actually it's probably more complicated than is needed. And after thinking for a while, we thought, well, some of this should be going on in any gap-driven two-component system. That doesn't have to be quantum. But it does have to be non-reciprocal. So I don't want to use a Hamiltonian, I want to use something which actually has, if you like, active matter. And in particular, I can have an active fluid and it's got non-reciprocal interactions and the force of A on B is not the same as B and A. And now we'll see if my machine is miraculously connected to the internet. Huh. Looks like it may. Oh, but you're not seeing this, so I'm sorry, I need to stop. So this is a model that we just built, and so these are radio-controlled robots. They come in red and blue form. Red ones like to align with the red ones, the blue ones like to align with the blue ones. But the red doesn't like to align with the blue, and the blue does like to align with the red. So there's competition. And this is an example of something that you can often see. Is that you see they're going around in opposite directions. It's chiral. The red ones.
No, they're both going counterclockwise.
Yeah, sorry. So they're both going counterclockwise. I'm sorry, but the chiral symmetry is broken because one is ahead of the other. Okay, right, yeah, right. Sorry. So the you know, if you let the model have overwhelmingly coupling of A bigger than B, they'll just stop in a line.
And this is your model of the U.S. Congress?
I hadn't thought about that. Actually, we tried this. So actually, I tried it. We tried it with some of our physics colleagues, and so what we decided we could do is that they should be agents, and we give them instructions, and that they were supposed to be walking together, and one's supposed to follow the other, and the other's supposed to do the opposite thing. Chaos ensued. I mean, what can I say? They want to take orders, right? So this is something that one can very easily build, and there are quite a lot of subtleties behind this. So I won't have time to talk about all of them. Actually, how am I doing for time?
About 15 minutes.
Oh, this is pretty good, I think. Right, so let me tell you what happens really in this model and in comparison to other ones, which are sort of which are causation models. Here are my two species, red and blue. And here is a parameter which measures the degree of non-reciprocity. Sorry, here is a parameter which measures the degree of non-reciprocity, and here's another parameter which says which is stronger than the other. So there are uninteresting regimes when this parameter is large in one direction or large in another direction, whether the system decides to align or to anti-align. As I tune this parameter down, I hit actually an exceptional point, and at that point, the solutions become chiral. And at that point, in this frame, they start to rotate. The rotation angle begins at pi over here and ends at 0 over here. And at the same point, the frequency at which they rotate goes from 0 to some finite number and back. I think actually it's intuitive that one might have things like this in this kind of model. Now, these robots are a bit of a cheat because their synchronization is static. They're not actually moving at all in this case. So unlike what I was telling you, that they are aligned, but there are other models you can do this for. So this is really a model of bird flocking. Again, it's called the Vic-shaped model. It may be known to some of you, but it has exactly this behavior. And here I'm plotting, if you like, something which you might think of as temperature. And there are these two parameters here, which is controlling the degree of non-reciprocity, which goes this way, and the degree, the overall interaction strength, which goes that way. If I'm at high noise, I just go from if you like, a ferromagnet to a paramagnet back to an antiferromagnet. That's fine. But if I'm now at much lower noise, I go from a situation where I go from aligned to anti-aligned in exactly this way, where this red line now is a set of exceptional points. And it turns out that there are some other phases in these models, which I think are perhaps interesting in their own right. And again, if you look at the steady state frequency going from chiral to align, that frequency vanishes at this point as they become to align. I hesitate to call it a time crystal. That's one of my co-authors did, so I don't really like that language. It turns out that this also maps into many other different kinds of models. This is a model of pattern formation. In fact, this is only one dimension, but you go from a phase here which, as a function of time in this direction and space, becomes ordered and develops traveling waves. Again, the transition from one to the other can be described in the same way. Look, maybe a technical point for those of you who understand dynamical systems well. This is very closely related to a Bogdanov-Tarkin bifurcation, for those of you who know it, which is associated with the appearance of two vanishing eigenvalues in the Jacobian or the Lyapunov matrix. What's special about this is not that we've done anything new for Bogdanov and Tarkins, but it's in an already broken symmetry state. So it's a second modification. Those analyses that I just showed you were mean field. So it turns out that most of the time, we're not sure whether it's all of the time, if you put back in space, you begin to get pattern-forming instabilities. And the reason is that generically associated with the structure here, as you approach the critical point, you find an unstable mode appearing in a finite K, which generates some kind of pattern-forming instability. I don't know whether that always happens. It happens in this particular mode because there's actually convection. And we're currently trying to study this in a lot of detail. So, the semi-conclusion is here. There's sort of a cookbook for this to understand what's actually going on, and we can go all of the way back to the problem I first showed you, is you've constructed a dynamical system, you find a stationary phase of spontaneously broken symmetry, then you do the natural thing that you do, which is to linearize about that fixed point. and then you will get some non-Hermitian operator L. Depending on whether the system has parity times symmetry explicitly broken, you will find within this space exceptional points with codimension 1, so that will mean lines in 2D, and that's what we saw in prediction models. And by the way, also in anti-cooperative Kuramoto models and things like this, we think it's sort of generic. If PT symmetry is explicitly broken, then there's another axis which corresponds to like applying a field, and then you get codimension 2 instabilities, which will be points in 2 dimension. And that actually corresponds to the case that I described right at the beginning of the Hermitian system of the laser. So when we wrote this, by the way, we thought that, well, what's requirement? There should be 2 or more components. There needs to be continuous and broken symmetry, non-reciprocal or non-Hermitian couplings. But in fact, lately we've discovered that it also includes transitions with coalescence of limit cycles. So all of these models have an explicit, some kind of rotational symmetry, U1 or U2, something like that. Just lately, we've been exploring models of coupled limit cycles, which I think are interesting in our case. So I think you all know what a limit cycle is. A limit cycle is when you have a trajectory which attracts, but it attracts in a cycle. So that means that there's a null Lyapunov exponent along it, because I can push it along that cycle and it costs me nothing to do that. But then there will be other Lyapunov exponents associated with the directions away from this. And of course the Lyapunov exponents are measured by putting a trajectory which is not too far away from the limit cycle, and if it pulls itself in, that's going to be attractive, and there may be other directions in which it's repulsive. So that depends on the side of this. One can ask, one can pick some models, and I think this is not too far-fetched to think that it might be interesting, where I have 2 limit cycles which are going to be brought together. So I'll take a model which actually has more than 1 limit cycle, and it will merge, and those 2 limit cycles will merge together, or I'll merge basically 2 stable and 1 unstable limit cycle into a single stable limit cycle. So how to do that? And we'll kind of look at that. And so again, what I'll be looking at is I tune some parameter. Because there are limit cycles around, there's always one eigenvalue which is 0, and then there should be another one which should meet, and that should correspond actually to, again, this coalescence. And as I'll show you, you can do this with some simple models. The simplest thing, and I apologize if this is a bit technical, but we haven't pretty much digested it yet, is to take a model where I take a pitchfork bifurcation. So I've got a dimension. So here's a Hopf oscillator. This is this. And I will introduce an extra parameter, which you can think of as going in the radial direction away from Z. And that parameter can have, depending on whether R is positive or negative, that parameter will settle down to either a non-zero value or 0. So it'll just find a minimum here. And then I'll couple these things to do. So I've got a pitchfork coupled to a Hopf. And here, something shows up that I don't think we properly understand yet. Depending on the form of this coupling, maybe whether it's even, odd, or even. In both cases, what I do find is that Lyapunov exponents join like this. So here's this critical point. And in this case, the angles between the Lyapunov vectors, the covariant Lyapunov vectors, also go to 0, so they align. This one has some more interesting topology, which I don't think we quite understand with, where in one direction it goes to 0, and in the other direction it goes to 90 degrees. So if anybody could help me with that, I'd like, there's some interesting topology associated with this that we haven't mentioned. So here's the neuron example, which I talked about. So to be quick on this, neurons are interesting for many reasons. This is one of the world's simplest models of coupled neurons. This is Wilson-Cowan neurons. And the idea is that you have two kinds of neurons in your brain. One is excitatory and one is inhibitory. Inhibitory neurons prevent their neighbor from firing, excitatory neurons like to make them fire. And you need both in order to produce dynamics. So here's the kind of simplest neural net model for things like this, which typically involve dynamical equations like this, exaggerating nonlinearity in a set of couplings. And here, this is actually just a simple model. There's only 3 neurons in this. But indeed, one can go through exactly this transition where the two, where you have 2 limit cycles that merge into one. And so there's an outer phase and an in-phase mode which come together and then become stable on this side. And this is of the previous class. This is of the class where you actually jump from parallel to perpendicular as you move across this. It works in Prerequisites models, never mind. Interestingly, as far as we can tell, this also works if you put in chaotic attractors. So this is a model of a couple of Lorentz attractors done in the same way as I did. So basically, here's the Lorentz attractor. I've got a coupling term to some other variable. The variable is a pitchfork. So I tune through the pitchforkian parameter, and this, of course, is much noisier. These are from simulations of a chaotic trajectory. So that seems to continue. And so this feels like a fairly generic possibility associated with this. Okay, so let me conclude. Sorry for going faster here. So the exceptional points of lines can form the boundary between different stationary states in non-Hermitian dynamical systems. I don't think that's necessarily always the case, but it seems to be really quite common. The thing that is interesting to me as a statistical physicist is to try and understand whether this transition really does correspond to some kind of bona fide phase transition, namely that there are unstable modes of divergent fluctuations, and I can characterize those in some traditional way. And certainly, if those universality classes exist, they're certainly different from thermodynamic phase transitions. So lastly, I should just say that all of this is a function of these folks. Yohanai, who's a postdoc of mine, who's now an assistant professor at the University of Kyoto. Michel Fouchot is a postdoc with Vincenzo, who's now actually moving to Paris. And 3 graduate students at Chicago. And explicitly Vincenzo, and as I say, it's always nice to be in an environment where I am now, where somebody who does quantum physics can talk to somebody who does classical physics, and we can figure out how to communicate and try to generate something. So with that, I will stop. And very interested in hearing questions, comments, and complaints, actually.
In the examples that you were showing us, the coupling seems to be one way, in the sense that the equation for W, the pitchfork, is not affected by the other equation.
Yes, and so I think that's not actually the case. So in the Wilson-Cowan case, I was really simulating equations where that isn't true.
Right.
I'm going to make a hypothesis that the pitchfork coupled Hopf, where I can orthogonalize those and make them one way, is something close to a normal form to the extent that I understand that, so that all transitions of this kind should be classifiable that way. I have no idea if it's true. So certainly it's, I mean, it's almost certainly not true in all cases, but it would be nice to see if one can classify this. And as I say, one of the things that I don't really feel that I understand is the topology associated with how I can get vectors that go around in a loop and come around 90 degrees out of phase in one case and 180 in the other. So there's some topology in that which we haven't excavated, and smarter people might well have it. But you're absolutely right. So I think I'm sort of making a hypothesis that separating those two variables into something which is normal and something which is not is okay. And by the way, what does that mean? It really means that if I've got a general model, of course, I've got some limit cycle, and the limit cycle is not a circle. It may be topologically a circle, but it's wandering around in space. And I've got another nearby limit cycle which is going to merge with it. If they merge, most of the time they have to merge continuously altogether. So it's not possible for them to join at one point if they don't join at all points. So if I make that hypothesis, then I would argue that in the vicinity of where they join together, I should have two sets of coordinates which I could define, which could be separately coupled. But that may be wrong.
In the example you spent a long time on in the beginning with the optical trap, you flashed some experimental results which were from 2012, so 11 years ago, in which you could see evidence of this transition in the parameter space. But I'm curious if that's been pursued, because you were talking about finding this critical point and whether it existed. Has anybody tried to find that, and what specifically would be interesting that happens there?
So I'm trying to persuade my colleagues to look for that. Right. So indeed. So what was specifically would be interesting first is does that point exist? I mean, I think that there's evidence that by changing parameters I can cut through space, and I see things which are either continuous or discontinuous. We'll have to change.
The alternative would be the line just continues.
Well, but I think the line could continue not forever, but actually we know that there are regimes of the experiment where it doesn't. There's a continuous transition. So what I'm interested in looking for is the spatial fluctuations. So to riff on that a bit, what we know in the regular polariton condensates is that they generically have a dynamical instability which causes them to roughen. Right? And generically, you can take the model that I wrote down, that time-dependent Ginzburg-Landau equation, and follow it through, and as you incorporate the nonlinearities, it turns into Carlo-Parisi-Zhang. So at least in 2 dimensions, where all of these experiments are done, what I expect to have happen, and this has been seen, is that the phase fluctuations begin to grow. They don't grow locally, they grow globally, so you can think of a rough surface, which is getting rougher and rougher. And the thing which is interesting to look for is then the characteristic spatial dimension versus the characteristic time dimension. So there's exponents which relate to correlation functions. And those things people have tried to measure. It's actually quite hard because it's difficult to get big enough systems. Right? But the hypothesis, however, is that that roughening transition should still exist, but the exponents would be different. Right? So that because you're supported by a set of modes which is in some sense much more unstable. So that's what I'd like experiments to look for in one or other of these models. And so I would say that I don't have anything to report on that, but I'm just, as I say, bothering experimentalists, and I hope they will succeed in doing this.
If they see the coupling, they won't lose their funding.
I presume not. I mean, I'd like to think that it would actually That's right. I'm not. By the way, what is this good for? I have no idea. But I suppose in this audience, I don't have to worry about saying.
So we started a little bit late, but I do want to be respectful of time. So let's wrap up for now, take further questions offline, and thank Peter once again.
If I think about neurons, so literally, I think about it as well, in the original, there's a broken symmetry, and things can go around to the right and then go around to the left. So the merging in that case is really important. Those two solutions just make the dissipation rise. Well, meaning they just light up. So the well, yeah, they will be synchronous, but in the rotating frame they won't be synchronous. So for example, the way to think about it is, if I was writing that load well, you know, that'd be a right-handed swab and a left-handed swab.
Go, be free.
Right. The system would, of course, with the presence of noise, have trouble deciding whether it wanted to be right-handed or left-handed.
Let's not jinx it.